Thanks for coming today. I'd like to talk a little bit about the moon by way of introduction. What I'm going to do is to kind of briefly give you an overview of what the moon is like, what processes have worked there, what the environment of the moon is like, and also what some of the landforms look like. In future talks in this series, we'll be going into much more greater detail on each of these, but for the time being, we're just going to call this an introduction to the moon. And I'd like to start off by basically giving you a rough idea of what the moon is like. And in a nutshell, this is my one view graph summary of the geology of the moon on one view graph. Basically, the moon is a rocky planet. It has a crust, a mantle, and a core, just like the Earth does. The difference being is that the proportions are different. If you think of the Earth, crust, mantle, and core, an egg is a good model. The yolk of the egg corresponds to the core, the white is the mantle, and the shell is the crust. And those are about the correct proportions. The moon is more like a raisin muffin. It basically has a fairly thick crust with a very tiny little core formed by a raisin right in the center. The core of the moon is only about 1% of the mass of the moon. And we're not really sure what it's made of. We think it's made of an iron sulfide, but we don't really know that for certain. The moon has a very heavily cratered surface. It was beat up and destroyed by heavy bombardment early in its history. And in fact, the outer surface of it has been completely pummeled by impacts ever since, therefore grinding up the surface rocks into this powdery material we call the regolith. The regolith is the soil that covers the moon. And that continues to form to this day, although at a very slow rate. Basically, the moon erodes about a centimeter every 20 million years. So things on the moon erode very, very slowly. The regolith is important because that's what we study and that's what we sample, and that, of course, will provide the feedstock for any resource processing that we might do on the moon. Now, compare the moon to some of the other terrestrial planets. These are some general properties. I put these on for your reference. I don't expect anyone to memorize them. But fundamentally, the moon is a body that's about 1% the mass of the Earth. Actually has one interesting property I have up here is moment of inertia. That actually measures the distribution of mass as a function of radial position within a spherical body. The moment of inertia of the moon is almost 0.4. A perfectly uniform sphere is 0.4 moment of inertia. So what this tells us as compared to the Earth, which is 0.33, that the core, again, of the moon is very, very tiny, if it has one at all. It has a very low escape velocity of only about 2.4 kilometers per second. It has extremes of surface temperature and effectively almost no atmosphere to speak of. It's effectively better than the best vacuum we can create artificially on the Earth. If you look at the moon, the near side is the side that's always facing the Earth. So as the moon rotates around us in a big circle, it turns at the same rate. Therefore, we only see one side of the moon at any given time. So there's a near side and a far side, which is the hemisphere of the moon that we never see. So these are what the two sides look like, and these are Clementine mosaics. So they're both taken at sort of a full moon perspective. So there's a full moon on the left for the near side and a full moon on the right for the far side. And what you notice is that the far side is very different than the near side. The far side has a paucity of these dark, smooth, lowland plains. There's two terrains on the moon: the dark, smooth, low Maria, which are the basaltic flood lavas of the moon, and the very bright, rugged, cratered highlands of the moon, the Terra. Maria and Terra form sort of the framework of the terrain on the front side of the moon. The far side is almost all Terra. There's very few Maria on the far side. This was actually first discovered in 1959 by the Soviet Lunar 3 probe, which flew around the moon and took our first pictures of the far side of the moon. You notice that very prominent crater on the far side filled with Maria with a bright central peak. That's the crater Tsiolkovsky, and that was one of the first craters named on the far side of the moon because it stood out very prominently in the Lunar 3 pictures. Now we know a bit about the composition of the moon, both from the rocks and from remote sensing from orbit. I've picked three maps here to kind of show the distribution of some key elements in lunar chemistry. Iron is in the top left, titanium is in the bottom left, and thorium is on the right side. Now, iron and titanium basically correlate with the Maria. The Maria are iron-rich basaltic flood lavas, and they're both rich in iron. Some Maria are very high in titanium, some are very low in titanium, and so what you'll see consequently in the titanium map is parts of the Maria have very high titanium, other parts don't. Iron is high in all the Maria lavas and very low in the highlands. So the basic dichotomy of the dark Maria and the light highlands is caused largely by the presence of iron. The amount of iron that's in the rocks determines how dark the surface rocks are. One thing you'll notice on the iron map is the far side of the moon has a very prominent circular patch of high iron in the southern far side highlands. And we'll be hearing more about that as we go on. That's actually the floor of the enormous South Pole Aitken Basin, which is the biggest impact feature on the moon. Basically extends from the south pole of the moon up to about minus 30 degrees latitude on the far side. Thorium, which is the one at the top right, that has a distribution that's a little bit different, and it's a little bit odd too, because all of the high amounts of thorium seem to be concentrated in the western near side hemisphere of the moon. Now, thorium is what we call an incompatible element. It's radioactive, so it produces heat, and also it doesn't fit into the normal rock-forming mineral crystal structures. Therefore, if you take a magma and you crystallize minerals out of it, thorium will be concentrated in the liquid up until the thing is 99% crystallized. And then thorium will be in what's remaining, what we call the last residual phases. It's called an incompatible element. And it's very concentrated in the western hemisphere, but notice also, again, the far side, the central floor of the South Pole Aitken Basin shows a thorium anomaly. So that's very telling about lunar evolution. In fact, the distribution of elements tells us a lot about how the moon formed and evolved. The environment of the moon is quite interesting. It's basically an airless body, so it experiences extremes in temperature. At noon on the equator, it can be 100 degrees centigrade. And at the darkest part of the night, just before sunrise, it can get down to minus 150. So that's a 250 degree temperature swing. Now the poles are a little bit different, because at the poles you're always having grazing incidents of sunlight. So sunlit areas there are about minus 50 centigrade, and might vary anywhere from 10 to 20 degrees. The dark areas near the poles, which don't get any sunlight at all, are extremely cold, and in fact may be less than 100 Kelvin, basically approaching temperatures 50 to 70 degrees above absolute zero. Now the significance of that is very important, because if volatile elements get into these very cold, dark areas, they're effectively there forever. They cannot be removed by any known process, and they're called cold traps. And that, in fact, is one of the reasons why the poles are interesting. We'll have a special talk on the poles later on in the series. Now, in addition, I also have some other properties listed up here: the amount of darkness, the resource potential. Basically, hydrogen on the moon is very rare. It's implanted by the solar wind largely, but also it might come from water-bearing impactors and meteorites and comets. At the equator, hydrogen occurs in concentrations between 50 and 100 parts per million. But at the poles, hydrogen is enhanced. We actually measured that from the Lunar Prospector spacecraft. And that suggests that something interesting is going on there. Either the low average surface temperatures of the poles are such that it retains more solar wind hydrogen, or you're measuring the presence of water that's trapped in these polar cold traps that I mentioned earlier. In addition, you can't see the Earth from the far side at all. You can see it continuously from the near side. The appearance of the Earth on the near side is you look up in the sky and the Earth is in a position where it never varies. Effectively, it's in the same spot all the time. So if you set up a high gain antenna and you point it at the Earth, it'll stay there forever. They did that on the Apollo 12 and 14 missions, where they set up an umbrella type S-band antenna. Now the far side, you never see the Earth because you're always on the hemisphere away from the Earth. The one area that's unique are the areas near the limbs, which is the 90-degree longitude, and the poles. And because there's an effect called libration, which I'll talk about in a minute, effectively you see the Earth only occasionally in those areas. The Earth appears to rise and set as it bobs up and down above and below the horizon. A slide a little bit more about the thermal conditions of the moon. You notice from this slide that we've got both Earth and Mars plotted, and the lunar temperatures, and these refer to surface temperatures, the actual temperature of the lunar surface, varies extremely from those two examples, largely because both of these other planets have atmospheres which help moderate the surface temperature extremes. An atmosphere acts as a great heat sink that allows it to maintain a much more equitable temperature between day and night. Now the moon doesn't have an atmosphere, so therefore any kind of space debris that hits the moon hits it at cosmic velocity. So effectively, things that hit the moon hit it at very, very high speeds. The RMS impact velocity at the moon is about 20 kilometers per second. So effectively, half the material hitting the moon hits at speeds greater than that. The other half hits it at speeds much lower than that. We don't really know what the flux is very well, but the estimate is that the impact hazard on the moon due to the natural micrometeorite flux is roughly a factor of 4 times lower than the flux we experience in low Earth orbit. Now the reason for that is largely because there's a lot of orbital debris in low Earth orbit. Exploded rockets, pieces of satellites, things that have decayed from higher orbits. And that orbital debris actually makes the impact hazard greater at an orbit of the ISS than there will be for a lunar base. I've included in here some estimates of the amount of flux, the number of craters per square meter per year. And you can see that that increases drastically as you go down in size. Effectively, the very smallest features, the very smallest craters will be the most abundant. And the distribution of craters on the moon basically follow a power law. So what that tells you is the very, very biggest craters are extremely rare, and the very, very smallest ones are extremely common. Now the moon is in an elliptical orbit, not a circular orbit, and in fact there is quite a bit of difference between apogee and perigee, roughly 40,000 kilometers, such that if you actually look at the apparent size of the moon between apogee and perigee, it's noticeably different. The moon at apogee is quite smaller than the moon at perigee, but in any event, a good average size of the moon in its orbit is roughly the size of a pea held at arm's length. It's about a half a degree of arc, which coincidentally happens to be the apparent angular diameter of the sun. And in fact, that's why we can have total eclipses, because the moon and sun are roughly the same size in an apparent angular size. The orbital period is 27.3 days, but from sunrise to sunrise, which is called the synodic period, the moon actually takes 29.5 days to go to that. So effectively, that's because the moon and Earth are orbiting together. And so as the moon rotates on its axis, it's also co-orbiting with the Earth. The spin axis of the moon is oriented nearly perpendicular to the ecliptic plane. So effectively what that means is that the poles, the sun is always at the horizon, either just slightly above or just slightly below the horizon. Now the moon's orbit has not been in this state for the entire history of the moon. In fact, the moon currently is receding at a rate of about 4 centimeters per year. That's been measured very accurately by the Apollo laser ranging experiments. Now, as you look at that, effectively, the reason this happens is that as the moon orbits the Earth is rotating faster. And so the tidal bulge actually precedes the moon's rotation, and therefore drags the moon along a little bit faster. So the moon, because the moon's orbital velocity is increasing, it's actually receding because it's going from a lower orbit to a higher orbit. Now, you cannot extrapolate this rate backward in time. When you do, you find that the moon and the Earth were together 2 billion years ago. So something unusual is going on here dynamically. We do know that the moon's currently at 60 Earth radii. It was as close as 40 to 30 Earth radii as few as 2 to 300 billion years ago. And we know this by actually measuring growth rings on fossil corals. You can actually measure, because they grow under a monthly cycle, you can actually measure the tidal periods of the ancient geologic past. And back in the around 2 to 300 million years ago, the moon was within about 40 Earth radii. Now, we don't understand what that effect has on the orientation of the spin axis. I mentioned earlier the spin axis is perpendicular to the ecliptic, but in actual fact, we suspect that the current spin axis has been stable for at least the last 2 billion years. So when we talk about the cold traps, the very dark, permanently dark parts of the lunar poles, we're talking about cold traps that have existed for at least 2 billion years and possibly longer. Now, that's significant because you need to know that these things are geologically old. Otherwise, there wouldn't be enough time to accumulate a significant amount of volatiles in these polar dark areas. Now, because the moon does come between the Earth and the sun, we actually have eclipses. The orbital plane of the moon is inclined about 5.5 degrees to the ecliptic, which means, and the Earth's spin axis is inclined 23 degrees. So effectively, what you have is that this line of nodes between the intersection between the moon's plane and the ecliptic actually shifts about 20 degrees per year, while the perigee shifts about 40 degrees per year. So therefore, eclipses occur at odd times, and in fact they occur only in parts of the Earth because the moon rotates around the Earth fast enough such that the duration of a total solar eclipse is only on the order of a few hours. And that point of darkest part, where basically the Earth is in the umbral shadow of the moon, actually moves across the Earth's surface as the Earth is spinning. So it's actually quite a complicated prediction factor, but we actually know this pretty well. The line of nodes, which is the only time you can actually have an eclipse when it crosses the orbital plane, goes on a cycle of 18 years. So effectively, that 18-year cycle, actually the spin axis of the moon is going to precess along that period of time. Now, the other effect that you have because of both the inclination of the orbital planes and the elliptical shape of the moon's orbit is an effect called libration. Libration basically means that the moon wobbles. Basically, it wobbles side to side. It's called longitudinal libration, and it wobbles back and forth, up and down. That's called latitudinal libration. The longitudinal libration is caused by the elliptical nature of the moon's orbit. As the moon moves out from perigee toward apogee, you're seeing a little bit beyond the trailing edge of the moon. Conversely, when it's coming from apogee toward perigee, you see a little bit from the leading edge of the moon, which is the western longitude. So the effect is shown in these two images. Mare Crisium is near the eastern limb of the moon. You see it at both the minimum and maximum longitudinal libration. You see when it's at maximum libration, you can actually see a little bit of the Maria right on the 90-degree longitude line, Mare Smithii, which is about right on the 90-degree line, whereas you cannot see it at all in the other case. Now, the other effect, the other librational effect, is latitudinal, and that's caused by the inclination of the moon's plane to the ecliptic and to the Earth. So effectively, you're seeing just a little, you're peeking just past the underside of the moon and looking just over the top side of the moon. And that effect is about 6 degrees. In both cases, there's a diurnal libration effect caused by the fact that the Earth has an apparent diameter. So at one point, when you see the moon, 12 hours later, at moonset, you're seeing a little bit, or an equivalent parallax from the diameter of the Earth. And that adds about 1 degree to the amount of libration in both cases. Now, topography. The moon is a very lumpy object. If you look at this topographic map, which is produced by Clementine Altimetry, you'll see the highest parts of the moon are about 8 kilometers above the mean lunar level. The deepest parts are about -8 kilometers. So that dynamic range, that range from the highest to the lowest, is about 16, 17 kilometers. Incidentally, that's the same dynamic range as the topography of the Earth. The Earth has exactly that same range. It's a totally different effect. On the Earth, we have a mobile planet where we have plates moving, we have plates being subducted in trenches, we have giant fold mountains thrown up by the collision of plates, and that forms quite a dynamic, active topographic model. But the moon's topography is caused completely by the presence of big old craters. In fact, the biggest range of topography you see on the moon is on the far side from the highlands northwest of South Pole Lake and down to the basin floor. That basically shows the entire dynamic range of topography on the moon. Now, physiographically, we have the Maria and the highlands. The Maria are pretty reasonably smooth at gross scales, at kilometer scales. They do have the occasional crater that you see. But as you get closer and closer to the moon, you see that the surface is saturated by smaller craters, craters ranging in size from hundreds of meters down to micrometers, literally. And that effect creates a very undulating surface on a meter scale. So on meter scales, the Maria and the highlands can both be very rough. But on macro scales, kilometer scales, they're actually quite different. The highlands have median slopes of about 7 to 10 degrees, the Maria about 4 to 5 degrees on the kilometer scale. I wanted to show the new map that we have. This is the map of the moon from the Japanese mission Kaguya, or Selene, and it confirms a lot of what we thought about the moon from the Clementine altimetry, but we've actually found the moon is even rougher than we thought. It goes from about 10.5 down to about -9 kilometers, so it really is an extremely rough, lumpy body. We also see on this image some very detailed topography on the far side. What it shows is a lot of quasi-circular features shown on the topographic map. Those are all basins. They're all old impact craters that have been so beat up and so pummeled by the impact bombardment, they're only present now, detectable by very detailed topography. This is our best topographic knowledge of the moon to date. It's a 500 kilometer contour interval. We'll actually have a better topographic model from an upcoming mission the Indians are going to fly called Chandrayaan, which I'll talk about at the very end. Now, geodetic control simply means that you know the coordinates of a specific landform or feature on the moon in inertial space. It's not particularly important unless you want to navigate on the moon. If you want to land on the moon at a certain coordinate and you want to be next to a feature, those are two different things. So in an ideal world, you know the coordinates of that feature to a gnat's eyebrow. You know it very well. But in actual fact, because of the piecemeal plan that we used to explore the moon with Apollo in the 60s, we don't know these coordinates very well. Now, near the near-side equator, we know the coordinates of landforms to within a few meters. We know this very accurately indeed, largely because of the detailed knowledge provided by Apollo. But as you move away from the equatorial zone to the higher latitudes, or you go around the moon to the far side, there can be offsets of multiple kilometers. In fact, when you actually, this map here on the bottom is the measure of the mismatch of features on the Clementine global base map versus longitude and latitude of the known lunar grid. And you can see that there are offsets exceeding 12 to 13 kilometers for parts of the far side. So we know that very poorly. And in fact, one of the key things that we want to get from the upcoming Lunar Reconnaissance Orbiter mission is a much better improved knowledge of this geodetic network, because that will allow you to send a spacecraft to a known coordinate, and you can be assured that it will be very near the feature that you want to investigate. Now, as I mentioned earlier, the moment of inertia of the moon is nearly that of a uniform sphere. However, it is slightly less than 0.4, so therefore a small core is allowed. We thought we detected a core with the Apollo seismic experiment, but that was only from one measurement from one event that occurred during the 7-year lifetime of that seismic network. We now think that there's a core because the Lunar Prospector spacecraft measured the influence of the interior of the moon on the geomagnetic tail. As the moon flies around the Earth, it goes in and out of the Earth's geomagnetic tail, and you measure a property called the induced dipole moment, which, because the core would be highly conductive electrically, should affect that geomagnetic tail with the direction of the flux lines. Lunar Prospector found that effect, and from that measurement, they estimate that the core is about 400 kilometers in diameter, roughly 1% of the mass of the moon, and consists, at least in part, of highly conductive iron. Now, in addition, when you look at a slightly shallower depth, the moon is very lumpy. I mentioned earlier that in terms of its gravity field. I mentioned earlier that the moon's lumpy topographically, but the gravity field varies quite a bit too. This particular model here shows Mare Smithii on the right side. Below that is a contour surface of the gravity field of Mare Smithii. So you see, although Smithii as a whole is indicated by the blue material at the top, it's actually a hill in gravity field, and that means that the gravitational attraction in the center of the basin is much higher than it is at the margin. Now, why would you have that? Well, one explanation is, as you form these craters, you excavate low-density crust, and the deep part of the moon, the mantle, which consists of denser rocks, in other words, more massive rocks, actually comes up to compensate for the excavated mass. And that forms a relief on what's called the lunar moho, the seismic discontinuity between crust and mantle. So you have these mantle plugs that extend up closer to the surface of the moon, making the gravity field stronger in the middle of the basin than it is at the edge. Now, these things are called mass cons. They were discovered by the Lunar Orbiter spacecraft in 1968. They cover all of the moon. They're associated with the youngest basins, typically, although Smithii is quite an old basin. And our best estimate of why they exist is this mantle uplift model. An alternative model is that you have a hole, you flood it with dense basalt lava, which is a higher density rock than the crust, and that causes a mass con. We don't really know which of those is right. We suspect the mantle uplift model is the best one because in the case of Mare Smithii, it has Mare fill, but the Mare fill is very thin. And you know that because the Mare and the highlands have different composition. You can see craters that dig down below the basalt and excavate highland material, which suggests that the basalts are thin. You can estimate the thickness of the lavas that way. All right, surface morphology. Basically, craters, craters, craters. They're craters on top of craters, and they range in size from things that are almost as big as the continental United States down to features that are submicron in size. There's a continuum of craters. They have all ages and morphologies, and they effectively cover the entire moon at all scales. That's one of the reasons why when the study of impact had undertook great momentum in the 1960s, because when we were going to the moon, we realized we didn't understand the physics and chemistry of hypervelocity impacts. And to understand the lunar samples that were going to be returned, we had to understand that process and how it worked in detail. So the simple fact is understanding craters and understanding that impact is one of the most fundamental geological processes in the solar system, to my mind, is the biggest scientific payoff we got from Apollo. Because of that, we understood that impact is indeed a fundamental process. In addition to impact on the moon, there were internal processes largely caused by the melting of the moon at deep interior and the eruption of those silicate liquids onto the surface to form these dark, smooth lavas that we call the maria. So basically, impact and volcanism, that's effectively what has formed the lunar surface. Now, there have been some minor processes. We form small domes through very slow volcanic extrusion. We do find faults on the moon where the crust has been deformed, and after it's been in place, you have a solid crust. If you push the crust together, you'll form ridges, like wrinkle ridges. If you pull the crust apart, you'll form cracks, which are faults, which are called graben. So basically, the two landforms, wrinkle ridges and graben, tell you about the stress history of that part of the moon's crust when those things formed, and they tend to have formed around 3 billion years ago. Since then, the only thing that's happened on the moon for the last 3 billion years is a continuous bombardment forming both big craters, but most importantly, the very small craters that ground up the surface into the regolith. You can have a lot of different landforms on the moon, landscapes. I just kind of picked some at random here to show what the moon looks like. The far view at the top left is a near full moon picture of the moon, of the near side showing the Maria and the highlands, and then the other picture is kind of taken from around the front side of the moon. The one at the top right is Lichtenberg. Now that crater is very interesting because it has rays, but it also has a dark Mare flow on the right side that's actually embayed the crater. Now you might say, well, what does that mean? Who cares? Rayed craters are the youngest features on the moon. When a crater forms, it has bright rays. Those rays disappear with time as the regolith gardens the fresh material and basically forms glassy regolith material on it. A rayed crater is young, and yet we think that lavas, the volcanic history of the moon ended a long time ago. Here's a rayed crater where the lava embays it, which means that the lava occurred after the rayed crater formed. So what's the implication? The implication is that lava is very, very young. In fact, that lava may be as young as 1 billion years old, which sounds like a long time, and it is in Earth terms, but in lunar terms, it's 1/3 the age of the youngest Mare lavas that we have in the Apollo collections. So that what this shows us is there's a lot that we still have to learn about how the moon has evolved and formed over time. I mentioned the two terrains earlier. Here's some basic facts about them. Typically, the Maria are lower average slopes on the kilometer scale, but they're blockier, whereas the highlands have higher slopes, higher average slopes, rolling terrain, but they're less blocky. Now, in a way, this seems kind of counterintuitive. If the rougher surfaces, you would expect to find more rocks. The reason that you don't is because the Maria, being younger, the bedrock, which is what the regolith has formed, is much closer to the surface. The regolith increases in thickness with time. As it continually bombards, the regolith, the ground-up layer, gets thicker. Now, because bedrock is close to the surface in the Maria, a smaller crater can excavate through the regolith down into the bedrock and bring up fresh rock. This particular view here is of the Apollo 11 landing site, and you can see those big boulders out there toward the horizon are actually a ray from a crater that Armstrong avoided during his landing. As he was flying in, the auto-targeting in the LEM was taking him right into the center of a big blocky crater. He took manual control, flew over that crater, and he landed just beyond the rim in between two rays. So on one side of the LEM there was a ray of blocks, on the other side there was another ray, which tells you that you can find block areas on the moon, but even within a blocky area near a crater ejecta blanket, you're able to find smooth areas that you can land on and use. Now the highlands are a little bit different, and the picture down at the bottom shows the Apollo 16 landing site. No, the LEM is not sinking into moon dust. It's actually behind a ridge, and that kind of gives you a feel for the rolling terrain of the Cayley Plains at the Apollo 16 site. But notice that, in fact, although there are rocks in the Cayley Plains, it's not as rocky as parts of the Maria. So, again, the terrain in the highlands, rolling, less rocks, Maria smoother, but more rocks. The slopes are actually have been studied quite in some detail. These are slope probability distributions. Don't get me wrong, you can find steep slopes in all terrains. I mean, the moon has a lot of rugged landforms. When you have a place where you have giant massifs that tower 10 kilometers above your head, you're going to have some steep slopes. But the simple fact is, like on Earth, although you have steep slopes, they're not common. And in fact, steep slopes in the Maria are actually quite rare. You only find them associated with fresh craters where you might have cliff faces in the outcrop exposures near the rim. In the highlands, it's all caused by very old features, many of which have been eroded to a great degree. You can have local slopes greater than 30 degrees in some places, but again, they're very rare. I'll talk a little bit about surface lighting. This is especially important if we end up going to the poles, because the poles and the lighting we experience during the Apollo missions are very different. This is a chart that basically shows the Apollo missions and what the sun elevation above the horizon were in different phases of each mission. And what you find is that the sun was lowest in Apollo 12, EVA-1, where it was about 7.5 degrees above the horizon at the beginning of the EVA. It was highest at the end of EVA-3 in Apollo 16, where it was almost 49 degrees above the horizon. Now, what does that look like? Well, effectively, here's two images taken at those two times. The first one was on just as Pete Conrad stepped out of the limb on Apollo 12, a 7.5 degree sun angle. You notice that cast shadows are very, very long. And so as you walk along, it can be somewhat confusing, both with your own shadow and the shadows cast by rock at small craters. Whereas the sun was much higher on the last EVA of Apollo 16, and in fact, the other thing you'll notice, and this is not an effect of the contrast stretch of these two images, is that the shadows are darker when the sun angle is lower than when it's higher, largely because as the sun angle gets higher, more of the surface is lit, you get more diffuse illumination of the shadowed areas. But even at low sun angles, you still are able to see in the shadow. The shadows are dark, but they're not jet black, simply because you have the surrounding terrain that's illuminated and you get the diffuse illumination. Effectively, shadows on the moon are illuminated from moonlight. The only thing is you're right on the moon and the moonlight is very, very strong. There's two panoramas showing low sun, both the up sun and down sun conditions. You have different challenges looking up sun or down sun. When you look up sun, you have a glare of the sun in your face, and so it's very hard. It tends to wash out. It reflects on your visor. It's very hard to discern things, but yet you have very good visibility to the left and to the right of the up sun direction. You can see the cast shadows very well. You can actually detect surface textures quite nicely. The challenge looking down sun is a little bit different. When you look down sun, you're near what's called the zero phase line. And if you look at the helmet at the top panorama, you look at at the very tip of the shadow is the astronaut's helmet, and you see this zero phase washout. Effectively, that effect is seen on the surface. It's also seen from orbit, and it's caused by the reinforcement of backscattered light by dust grains that makes this very strong backscattered effect. It's called the coherent opposition backscatter effect. It's very hard to look down sun at zero phase. In fact, it's this very effect that we're going to use with the radar on these orbital experiments to look for polar ice. The same effect, same principle, only using radio waves instead of sunlight. Now, can we work in the dark? Well, there's a lot of bits of evidence that suggest that might actually be feasible. Dean Epler did a study back in the 1990s looking at the effects of a full Earth illuminating the near side of the moon, and he found that it was very similar to working in a room with a 60-watt bulb suspended 2.2 meters overhead. So that's actually quite a bit of light. Remember, the Earth not only is much bigger than the moon, it's about 40 times as bright as the moon. And that's due both to the big apparent size of the Earth compared to the moon, but also to the fact that Earth's albedo is much higher. The Earth's albedo is high because it has clouds and water which reflect much more light. The average albedo of the Earth is about 0.4. The albedo of the moon is about 0.11. So the Earth is very bright from the moon and in fact would illuminate the terrain with kind of a nice bluish cast light. So it would be very similar to working in a poorly lit room. Now, if you're in the poles and you're in permanently dark areas, there's no illumination there at all. The only light that you get is from starlight and from the occasional peak that you can see nearby that might be like the rim of a crater or a mountain that's outside your cold trap. Work in those areas is going to require artificial lighting, so we're going to have to be prepared for that eventuality. I want to talk a little bit about the regolith. The regolith is, of course, the ground-up surface layer of the moon caused by impact bombardment. One thing I want to emphasize, the regolith includes everything. It's not just the very fine material that we call the soil, but it includes the rocks and boulders, too. The definition of regolith is just unconsolidated debris that lies on bedrock. And on Earth, it can be caused by many things. It's typically caused by chemical weathering and even biological activity. On the moon, there's only one thing that causes regolith formation, and that's the pulverization of the surface rocks by micrometeorite impact. You can see from these images that you can get quite a wide variety of different local terrains on the moon. All this material is regolith. All of it is ground-up surface layer. The picture at the top right is Hadley Rill from the Apollo 15 landing site. The rover is right on the edge of the rill. It's looking up north as the rill trends away from the landing site. It's very deceiving because there's no atmosphere on the moon. There's nothing to provide scale. Features that are tens of kilometers away look as fresh and as close as if they were 100 meters away. So when you look up Hadley Rill here, it looks like it's just a nice little rolling terrain, but actually the far edge of that rill is about 20 kilometers away. And the rocks that are lining the bottom of the rill that you can see right in the bottom that have rolled down from the top, some of them are as large as a house. Some of them are 20 to 30 meters across. So it's very hard to get a sense of scale when you're on the moon. The only thing that provides scale are man-made objects. And so the visibility is superb. You can see for great distances, and you can see with great clarity. But if you're going to use that to judge, to walk to a place, you want to walk over to this boulder and sample it, it's going to be very difficult. In fact, there's a very memorable scene in the EVA-3 of Apollo 16 when they went to North Ray Crater, and John and Charlie are walking toward House Rock. And it starts off, the TV shows the astronauts walking toward this thing, and there's a rock sitting there, and it looks like it's very close. But as they continue to walk, they walk for about 5 minutes, and they keep getting tinier and tinier and tinier, and you realize that it's very difficult to judge your distance on the moon. The regolith is very fine-grained, and when we talk about the regolith now, I'm going to basically focus on the finest fraction, because that seems to be what has people most concerned. The average grain size is about 70 microns, and you think about that, that's roughly the same grain size as talcum powder. So talcum powder is actually a good size analog to lunar soil. It is not a good analog to its abrasiveness. Talc is very soft. It's the softest geological material we know. The problem with the lunar regolith is that it's very, very hard because most of it is glass. In fact, if you look at the Apollo 11 regolith, the first mission that was brought back from the moon, there's one soil that is more than 75% glass. And it's all caused by impacts hitting the moon, flash melting the minerals there because they come in at such great velocity. They vaporize and they form these glassy things that weld together bits of themselves, bits of minerals, bits of rock. These are called agglutinates, and they're basically glassy aggregates formed by micrometeorite impact. The older a soil is, the more of these agglutinates will accumulate. And so when they get broken, they don't break in nice, smooth, rounded forms like sand grains. They become very angular, they're very jagged. The high specific surface area, that basically refers to a comparison to spheres of the same surface area. Lunar's specific surface area is 8 times that of spheres with the equivalent size range. And what that tells you is that the fragments of the lunar soil that are making this up have all these crenulations and angles and facets. And that's one of the reasons why if they get into moving parts, the moving parts stop moving, because it's very abrasive and very, very difficult to deal with. And it gets into everything. Effectively, the Apollo astronauts found it as the longer they were on the moon, the dirtier they got, the harder it was to make moving parts work, and the harder it was to keep things clean. In at least 2 cases on the moon, the fenders broke off the LRVs. The problem with that is as the wheels turn, they kick up soil. If there's no fender, the soil forms a rooster tail that soon coats the astronauts and their equipment with dirt. And if especially things like the electronics unit on the LRV got covered with dirt, it would soon overheat and it would soon quit working. So they had to continually brush off the TV camera, the crew, the relay unit, and their own suits and backpacks in order to keep reasonably clean. The picture of the gloves down there at the bottom, even today, those gloves, the soil is so fine and so abrasive and so clinging that they cannot get all the lunar soil out of anything that went to the moon. Anything that went to the moon has bits of the moon embedded in it. If you look at them in the museums, you can actually see it. This regolith has an unusual structure because of this grain size. If you actually walk out on it, it seems very loose and fluffy. And this was noted by actually Armstrong and Aldrin on Apollo 11. When they first stepped on the moon, they kicked up the soil. It was nice and fluffy and loose. Then Aldrin tried to pound in the flagstaff to plant the American flag. And as he kept hitting it with a hammer, he noticed it wasn't going in very far. So it went in easily for the first few centimeters, and then it gets very, very dense. The density, basically, the high density area starts anywhere from 5 to 10 centimeters below the surface. And it's caused by this highly angular nature of the dust. What happens is, as you go down in the regolith, these grains, these highly angular grains, become interlocking, and they get very tightly packed. And because the moon is only exposed to this meteorite bombardment with the small pieces dominating, that packing starts very close to the surface. It starts about 10 centimeters below the surface. So the upper surface is loose and fluffy. Once you get down into that, it's very, very dense. Now, a question about levitated dust. This has come up because there are some observations from Apollo and Surveyor suggesting that dust on the moon might actually float on an electrostatic charge. We're actually talking about two different phenomena here. On the left was something that was observed on Surveyors called horizon glow. And what they noticed is that after the sunset, anywhere from 50 minutes to several hours after the sunset, if they took an image, they would notice that the horizon was visible. And the horizon was visible, it looked as though it was being illuminated. Now, this cannot be a sunlit peak in the distance, because the sun is actually below the horizon here. It's not the solar corona, because we know what that looks like. This actually appears to be caused by material that's actually floating above the surface of the moon at an altitude of a couple of meters. So in other words, it's a very thin zone of dust that's suspended. Now, because there's no atmosphere on the moon, it can't be an aerial phenomena. It's got to be something dealing with electrostatics. And the idea is, as the terminator moves across the lunar surface, it induces a charge. It's negative before sunrise, it's positive after sunrise. And that can actually cause an electrostatic charge that would cause the very small micron size and smaller particles to actually float above the surface for a very short period of time. Now, the other thing that we know that was observed, it was observed by the crew of Apollo 17, specifically Gene Cernan, who actually made these sketches that are in the middle. What he observed was, before sunrise, you saw streamers of the sun, but you also saw on each side of the corona, before the sun actually appeared, you saw a brightening on the limb. And he actually sketched this out. That was the observation. And he didn't, and Gene was a good observer, and he didn't try to explain it. He just made sketches and made the observation. When he came back, people grabbed on this and said, well, we know what's happening. There has to be scattering of light from the sun before sunrise due to the presence of levitated dust. And again, electrostatically levitated dust was invoked to explain this. You should keep in mind these are two different phenomena, because what we see at the Surveyor site is meter scale, meter to tens of meter scale. What Gene Cernan saw from orbit, whatever it is kilometer scale, and actually tens to hundreds of kilometer scale. Because in fact, you can see this scale drawing by Dave Criswell over here on the right side. You're talking about a fairly big area, fairly high above the moon doing this. Now, I personally think that what Cernan saw was not lunar. I think actually what he saw was zodiacal light, which is the light scattered by the sun caused by the cloud of debris that co-orbits with Earth and Moon around the sun. Basically, the stuff that pummels the moon, the micrometeorite bombardment, is caused by this stuff. It's actually disaggregated meteoritical material that forms a big dust cloud that we orbit around the sun in. And I think that's what he's seeing here, but we don't know that. And we don't know what's causing this. We don't know if it's lunar, and most importantly, we don't know if it's an important issue or a hazard for future trips to the moon. So we have to find out what it is. Now, there's some lines of evidence, in fact, that levitated dust is not a significant problem. I'm going to cite three of them, and you can judge their veracity for yourself. First, we do have a long-duration exposure facility experiment on the moon, and that was Surveyor 3. Surveyor 3 landed on the moon in 1966. The Apollo 12 astronauts visited it 30 months later, and they returned pieces of the Surveyor to Earth for analysis. To everyone's amazement, they actually found a bacterium on one of the TV cameras. We're still not sure to this date whether it was actually survived its 30 months on the moon or whether it was some contaminant in the handling of the equipment coming back. But the evidence, as near as we can tell from these parts returned of the Surveyor 3 spacecraft, was that there was no lunar process that put dust on the parts. When the parts came back, they had dust on them, but they had dust on them because the Surveyor spacecraft was in a crater. The Apollo 12 limb came in just to the right of that crater. It was blowing dust from the descent plume from its engine, and that dust kicked over parts of the spacecraft. They know that because when they looked at it, the parts that were exposed to the limb plume were coated with dust, but the parts that were not exposed were not coated. So they concluded that the only thing that coated these things was caused by the lunar module, not by any indigenous lunar process. Now remember, this thing was spent 30 months on the moon. So if there were this process of levitated dust depositing itself on things that are on the lunar surface, we did not record it with the Surveyor spacecraft. There are other things too. We have the lunar laser ranging retroreflectors, which are basically glass arrays, mirror arrays, that were laid out on the moon. The one on the top is the Apollo 11 laser reflector. The one on the bottom is the Apollo 14 laser reflector. A key thing to keep in mind, when you send a laser pulse to the moon and you get the reflection back, there's a very high degree of attenuation because you've got a very long path length. You know, the inverse square law still works. So you can blast a laser to the moon and you can get a return. That return is very, very weak. And it was weak from the very day these reflectors were actually deployed. However, they have been using these for the past 35 years. And to date, they have not particularly noticed any degradation in their performance. Now, I've since been told that there has been some degradation noted. I don't know how much stock to put in that. I do know that the actual amount of photons measured from the reflections was never done. They actually never measured them from the beginning and continued to measure them for 40 years. However, they're still using these reflectors and they still get good returns from them to this day. So that suggests that whatever's happening on the moon, you aren't having a continual application of dust to these surfaces. Those surfaces are still relatively clean because we're still getting a good reflection from them. The last thing is even more impressive, and this is something that's quite interesting. On the moon, when you're forming the regolith, you're grinding up the rocks, but you're also throwing sprays of material. When you form a crater, you throw a spray of material out called ejecta, and it comes out in an umbrella fashion and coats the terrain around it. Now imagine that process times several million, and you can see that you're constantly moving material back and forth by small impacts. Now, if lateral transport were significant, you would expect to see a contact where you have one type of rock unit against another type of rock unit smear out with time. Effectively, basalts are very high in iron and highlands are very low. So you have a Mare highland contact, you would expect to see a nice gradational change between those two. But you don't. Now we're talking about areas here, and this is Mare Crisium. Those lavas are 3.5 billion years old, and they're abutting against 4 billion year old highlands. And if you look in the chemical data, that is a razor-sharp geologic contact. In other words, that contact is probably as sharp as it was the day it formed. And that suggests that you're not getting dust rising up above the surface and then moving and then coating another surface. Because if you were, this contact would be smeared out. So I think this actually is compelling evidence that you don't have a significant amount of dust transport. Talk briefly about the origin of the moon. There are three traditional models. Intact capture postulated that the moon formed somewhere else and then swung by the Earth and was caught into Earth orbit. The fission model suggested originally the Earth was nearly molten, it was spinning very rapidly, it split off, and that the two pieces became Earth and Moon. And finally there's the binary or co-accretion model, where you're forming all the planets from smaller debris. Earth and Moon both accreted separately as independent objects at about 1 AU. Now the problem with these three models, and these were the models before Apollo, and they were actually the models for about 20 years after Apollo as well. None of them are satisfactory because all of them have some problem. Either they don't match the known dynamical properties of the Earth-Moon system, or they don't match the chemical features of the Earth-Moon system. So about 1984, as we were mapping the moon, we found that we kept finding bigger and bigger impact events. The South Pole Lake and Basin that I showed, that's one of the biggest impact events we found. So that tells us that large objects did collide with the planets early in its history. And it was a short jump from that idea to the idea that you might actually be able to solve the dynamic problems of intact capture and at the same time explain the similar chemistry of Earth and Moon that we found that supported things like binary accretion by something called the giant impact model. Now this model, effectively 4.5 billion years ago at one astronomical unit, you didn't have one planet, you had two planets. You had something called the proto-Earth, which was about 90% of the current Earth mass, and you had another object that they called Theia, it actually gave it a name, that was about the size of Mars. Both planets had already been differentiated into crust and core. And Theia had a glancing encounter with the Earth. It basically hit the Earth at an angle and shot a jet of debris, vaporized rock, at such a speed that it actually went into Earth orbit. So Theia and the proto-Earth combined to form the modern Earth, but that jet of vapor that was squirted into Earth orbit formed a ring of debris, and that ring of debris later accreted into the moon. The interesting thing about this model is it simultaneously explains known facts about the chemistry of the moon in broad terms, and it explains the very strange dynamical properties of the Earth-Moon system. Earth-Moon system, first of all, the Earth and Moon have a very high mass ratio. The Moon's about 1% of the Earth mass. If you look at the Galilean satellites of Jupiter, those satellites are a minuscule fraction of the mass of Jupiter. So something unusual is going on when you have such a large moon. You can accurately refer to the Earth and Moon as a double planet. But more than that, the strange inclination of the orbital planes and the large amount of angular momentum in the system call for some unusual process. And the giant impact idea was actually proposed because it explained a lot of the unusual processes of the moon with a fairly minimal amount of special pleading. Now since then, right after the moon formed, it accreted so rapidly, it accreted from very small objects that were already in Earth orbit, it released a large amount of thermal energy and completely melted the moon, forming what we call the magma ocean. Then the magma ocean, low-density minerals floated to the top, high-density minerals sank. And what that meant was you got a crust that was rich in low-density calcium aluminum feldspar, and the mantle, which was later melted to form the Mare basalts, was rich in iron and magnesium. So this model of the magma ocean sort of explains, to first order, the geochemistry of the moon too. Basically aluminum calcium-rich crust with occasionally flooded by small amounts of iron-rich lava. After that formed, after the crust formed, you had a heavy bombardment forming very large basins, and it formed the moon as we have today. You formed a very heavily cratered highlands, partially flooded it with lava, and then basically had impact cratering since then. That's a very quick thumbnail sketch of lunar history. You'll get much more detail on this in the later lectures in this course. I want to close by briefly talking a little bit about robotic missions. We actually had an amazingly impressive series of robotic missions to the moon, largely to support the Apollo mission, but even since then we've had some very good missions that have given us a good picture of how the moon is formed and evolved. Basically they fall into three classes: impactors, which are hard landers basically slammed into the moon; soft landers like Surveyor that gently set down and made measurements after landing; and finally orbiters, which initially were sent to get high-resolution photographs to support manned landings, but ultimately carried sophisticated remote sensing instruments that allowed you to measure chemistry and other properties from orbit. Now, in addition to those missions that are in the can, if you will, we actually have 4 missions going to the moon in the next few years, 2 of which are already in orbit. Japan has the Selene or Kaguya mission, which is currently orbiting the moon. It has been since last fall. The Chinese have a mission they call Chang'e. Both of those missions are now orbiting the moon. Kaguya is in a polar orbit 100 kilometers high. Chang'e is in a polar orbit 200 kilometers high. Both of them are taking images. Both of them are making altimetric measurements. Each one has a little bit different spin, although all these missions are carrying similar instruments. Each one has a slightly different twist, reflecting the specific interests of each country. Japan's interests are to make the most detailed, comprehensive maps known of all different properties: chemistry, mineralogy, and geophysics. The Chinese are actually mapping the surface morphology of the moon and actually probing the subsurface using microwave radiometry. That's a unique experiment. That's the one thing they're doing that no one else is doing. Chandrayaan-1 and Lunar Reconnaissance Orbiter are 2 missions that are yet to be launched. Chandrayaan-1 should be launched later this year. That's being flown by India. They're flying, they have 11 experiments that do just about everything known to man, including measuring the chemistry and mineralogy of the surface. I actually have an experiment on Chandrayaan-1. We're flying what we call the mini-SAR, which is a synthetic aperture radar. We're going to use that radar to map the dark areas of the poles and to look for evidence of ice. The NASA Lunar Reconnaissance Orbiter is primarily dedicated to geodesy, that thing I mentioned earlier where you want to know the coordinates of features to high precision. It's going to measure the topography of the moon to great precision and also give us a good geodetic control net. In addition, it's actually flying experiments designed to look at the polar issues and polar deposits. We're going to measure the temperature of the cold traps. We're going to measure the neutron flux to actually see where the high hydrogen might be occurring. And in addition, we're flying a version of that mini-SAR radar on LRO as well. So what might that all mean? Well, what I've done here is kind of list what we various properties that we might want to know from an orbital mission. We want to know the shape of the moon. We want to know where features are positioned. We want to know the morphology, the landforms that make it up, the chemistry and the mineralogy, the gravity. These are the properties we want to know. The middle column sort of gives us our current knowledge, and our current knowledge is actually quite good. We actually have a fairly good knowledge globally of the moon, thanks to Lunar Prospector and Clementine, for most of these things. The future column shows what we're going to have after all 4 of these missions return their data. And I have to say, as a practicing lunar scientist, this is going to be a superb data set. We're really going to know quite a lot about the moon in great detail from all these missions. And I think ultimately all of them will probably make their data available, and we'll be able to share them and actually get quite a good insight into the history and evolution of the moon. So I'll close here. I do have some suggested reading. Now, most of these I have hyperlinks. Some of this stuff is available for free. For instance, the first reference, Don Wilhelm's book, you can actually get to that on the web and download it. It's in PDF form. The other ones I've listed are available from Amazon and any good bookstore. They'll give you a good overview to the moon, what the moon's history has been, what processes work, and what the moon's made of. And I'll stop there. Thank you.